Hi everybody, welcome to lecture 6 of Professor Goswami.
Okay, thank you, Rama, and welcome everybody to the sixth lecture. Today, I'm going to talk about Indian monsoon and overview of mean and variability. So basically, this lecture is about observations, what the monsoon is like in terms of its three-dimensional structure and some space-time variability. So this is because this is because why do you want to study the mean and variability of the monsoon? This is because monsoon is one of the largest rain-bearing climate system in the world. Many civilizations have just evolved around it, and there is a lot of evidence of that from. And the economy of the livelihood of about 1.5 billion people depend on it, and therefore the predicting the monsoon rainfall at least one season in advance and maybe longer than that is a great science question and of great with a lot of social therefore, but this prediction of the monsoon depends on, or the skill of the prediction of the monsoon or the limit on predictability of the monsoon depends on the structure of the mean and the amplitude and the signal of its variability, because that signal, the prediction depends on the signal to noise, and therefore the signal we have to quantify. And today's what I'm going to do is to just basically today try to quantify this signal of the structure and the signal of its variability, and that's what I'm going to do today. And therefore it is all from observations, and today we'll set the stage for asking questions. So what do you want to know about monsoon? What are the questions that we need to know? And that will be to do that. Actually, we have to have this from observations. What is its structure and what is its variability, and those are the things that we need as a base to ask those questions. So I'm going to talk about the Indian monsoon as a phase of the monsoon annual cycle. This is nothing but there is a seasonality. Seasonality is the key to monsoon, and therefore it is part of the annual cycle. And so we'll talk about how the monsoon is a part of this annual cycle, then some of the basic characteristics. Then I'll talk about some year-to-year variations and some link with the El Nino and sudden oscillation. Then I'll talk about interdecadal variations. So sort of there are some multi-decadal oscillations of the monsoon, and then it's a link with the North Atlantic SST. Then at the end, towards the end, I will talk about how it is relevant to the prediction and predictability. And that relevance comes from how models, for prediction and prediction of monsoon, you need a model, a coupled model. And the coupled models have their own problems. They are never perfect. And so how the imperfection of the model affects the prediction and predictability, and that I'll try to give what is the status on that currently, and how we can improve. So therefore, understanding the nature of the monsoon variability will help us to improve the models so that the models can be, eventually make a better and better prediction. So to start with, to understand monsoon, we have to understand the environment where the monsoon takes place. And the monsoon takes place in the environment of this Indian continent, being surrounded by mountains, the high mountains in the north, and the warm oceans on the three sides of the continent. And so this is an unique geographical location on which monsoon actually takes place. And these mountains have their own interesting characteristic structures, and these structures have important bearing on the rainfall formation process in this region. For example, the Himalayas is very tall, and this is our Ganges basin, and this is Brahmaputra basin, and it is surrounded by these horseshoe-shaped mountains, and this really affects the rainfall over this region. So the rainfall in this region is very much affected by the flow of air, bringing moist air from the Bay of Bengal and affected by these mountains. Similarly, here we have Western Ghats, and these winds come and hit the Western Ghats, and therefore they have to go up and they will produce rain. So this orographic rain is an important component of monsoon, and this orography plays a great deal in terms of the distribution and the intensity of the rainfall in this region. And it is also affected by the oceans to the south, where it happens to be the warmest in the world, because we are part of what is known as the Indo-Pacific warm pool. From the Western Pacific to Eastern Indian Ocean, there is a warm pool which is the warmest in the world. And this warm pool extends to the Indian Ocean, and therefore most of the time our ocean to the south is pretty warm. And there, during the monsoon, due to the winds interacting with the ocean, it cools down to the west, but still a large part of it is very, very warm. The warm ocean means availability of moisture. A lot of moisture is available. There is a lot more evaporation. This evaporation is brought, the moisture is brought to the continent, and therefore convergence of moisture can lead to more convective activity and rainfall. And so this combination of warm ocean and the land, which gets heated up faster, and therefore a lot of convective activity there, and therefore the availability of moisture helps forming convection over land. And with the mountains in the around, there is a huge interaction between the orography and the moisture producing rain over this region. So this is important part of our geography. Let me just bring this down. But monsoon is essentially a seasonal phenomenon, and the seasonality is very important. The whole name monsoon comes from the Arabian word mosim, which means seasonal winds. So in one season the winds is one way, the other season the wind is other way, and this change in winds is characteristics of the monsoon, and that was recognized way back. And there is reference between using these winds were known by the mariners in the very, very early days, and even as early as AD 45 to 47, Greek navigator Hippolytus, there is sort of historical record somewhere saying that they used these, they discovered these changes in the winds and then used them effectively for trading. For example, in one season they will come in, and then when we go out in another season, making the sailing ships make use of effectively the wind during these seasons. So these winds, seasonal changes in the winds were known for a long time. And these winds are part of a strongly connected with the global ITCZ. Our monsoon and the winds are connected with not just regional phenomenon, but it is connected with this global ITCZ. So this is a global rainfall pattern. The mean rainfall during July and basically summer, roughly this is similar. And so it is this global band of rainfall is known as the ITCZ, and that ITCZ is a region of wind convergence almost everywhere, and therefore here in our region,
could you tell what ITCZ stands for?
ITCZ is known as is a short form of what is known as intertropical convergence zone. So basically from this northern hemisphere and southern hemisphere wind converge, and this convergence produces the moisture convergence, and that moisture convergence gives rise to these rains. So these rains are associated with this conversion, intertropical. So between these two tropical belts, here also you can see. In monsoon, there is a bit of difference because of the rain belt moving northward. So it changes slightly. There are two ITCs, one at the land and one over the ocean. So it is still a part of what is called a intertropical convergence zone, and that is global. And but this is a regional manifestation of that convergence zone. And that is in this winter again. You can see that this rain belt is to the south of the equator, and this is also a convergence zone. And there is of course another bend in the to the north, weaker. There is also a convergence zone. So this is a part of a global structure of the intertropical convergence zone, or ITCZ. Sometimes people call it tropical convergence zone. So monsoon is part of a globally convergence zone, and that is important to recognize. So having said that, so let us see what the monsoon is. Therefore, although monsoon was identified only with the winds in the beginning, we cannot describe monsoon or conceive monsoon today without the association with the rainfall, because rainfall and the winds seem to be very much convectively coupled. They are very much coupled. So Indian monsoon we can define, instead of just saying that that it is intertropical convergence zone, which used to be the only definition in the beginning. Today we know that the rain and the winds are very strongly coupled. Therefore, we can say that the monsoon is a convectively coupled system arising as manifestation of the seasonal northward migration of the rain band or the tropical convergence zone. So this is a sustained animation of that. So where I have used climatological mean rainfall, and then how this rainfall evolves with the season and moves northward. Every 10 days I have plotted that, and so it goes rather quickly, and then comes back in the winter again to the south. And the summer, this rain band, and you see that winds are a low level winds I have plotted, and as you can see, as the rain band moves to the north, the winds also change, and they produce this vorticity in this region. Again, then the retreat, the winds again come, and they are always associated with this rain band. So that coupling is the convective coupling I am talking about, and so therefore regionally also in this region, the monsoon is a manifestation of the seasonal migration of this convergence zone or intertropical convergence zone, and that seasonal convergence, seasonal migration is associated with seasonal changes of the winds. And this is part of the annual cycle, as I mentioned that. So if I plot the annual cycle of rain over the monsoon region, it has a clear annual cycle. The summer is very wet, and winter is almost dry, very little rainfall, and therefore this is part of this annual cycle. And how do I define the season? And there is no clear way of doing that. Basically, since this is part of the annual cycle, so I can use the amplitude of the annual cycle. So this amplitude is like 11 millimeter per day. And that amplitude, if it exceeds 60% of more than 60%, roughly, you can say that the monsoon season has started. This is a very, very, very crude way of, I mean, that is how traditionally a definition of the monsoon season has happened, and it sort of remains. We can clearly see, of course, that from in June there is a rather sudden increase of rainfall, and then from June to September there is enhanced rainfall, and there is again October the rain significantly decreases. Therefore, there is some rationale in defining monsoon. Exactly why the June 1 to 30th September is not very well clear from this. And later on in my next talk, I will define more quantitatively the sort of rainy season. So this is about 60% of that, and then. So monsoon, monsoon basic characteristics of monsoon is that that during the summer, we have a ITCZ or the rain band over here. This rain band it becomes tilted from southeast to northwest because the rain band has moved to the north in this region, but not so much moved in the other regions. As a result, the ITCZ becomes tilted. So this is an important characteristics of this monsoon. But a secondary ITCZ remains here. So there is another ITCZ that remains there. So the monsoon is one important characteristics is that there are two locations of ITCZ during the monsoon season, summer monsoon season, and this plays an important role. So there is so much rain means there is also some ascending motion here. There is so much rain means there is also ascending motion, but this happens to be stronger than this, and therefore we have overturning circulation from land to the south, but in between there is also a weak ascending motion in between. And this is an important, and because of these two favorable positions of the ITCZ, on subseasonal time scale, there can be competition between these two, and one can be sometimes stronger and the other can be stronger, and so on. This is what produces our subseasonal oscillations. We'll talk about that in the talk when we discuss the subseasonal oscillations. And of course, in the winter, the ITCZ moves down to the south, and then the land becomes very dry. So now the land is very wet, and the summer land is very dry. And so these are kind of, and then there are two other characteristics within the region. There is a sort of rainfall maximum west of the Western Ghat. This is due to the orographic effect of the Western Ghat. And there is also a rainfall maximum zone in the Bay of Bengal, and not exactly over and over the Northeast India. So this Northeast Indian Bay of Bengal is another maximum rainfall region. So this is also an important characteristics of our distribution of the rainfall. This why monsoon rainfall becomes maximum over the North Bay of Bengal is a question that we'll have to address separately. But over the northeastern region, of course, the moisture fed from the Bay of Bengal with the orographic effect produces heavy rain in this region. So, but important point is that, okay, there in northeast there is a maximum, and there is Western Ghat there is a maximum, but there is a gradient from northeast to the south, southeast to the northwest, and that is also an important characteristics of the monsoon. So we have to remember that. So the western part is drier, the eastern part is wetter. So let us now look at some of the annual cycle of this ITCZ. Now, suppose I look at the average the daily precipitation between 70, the 70 degrees here and 90 degrees here sort of represents our major portion of this. Suppose I average the rainfall during this band daily, and see how this rain band moves around. And if I do that and plot it as a function of, this is a climatological sort of long-term mean, daily long-term mean rainfall. And obviously this means that in the winter, the rain is south of the equator rain band and remains there almost up to May, April. And in the May, it starts moving northward. And then somewhere in the June, in the beginning of June, there is a jump of rain going quickly, and this is what we call onset of monsoon. So there is a jump in the rain also moving northward, and that then goes and establishes itself by about 20-23 degrees north, and then subsequently then in September it starts coming down. So that is the annual cycle of the ignite. But while there is a maximum here during the summer, there is also a maximum in the about 5 degrees south, which was the climatological mean position here. So at that point on a daily scale also, a ITCG remains there. So that is the, I'll come back later on. So this is kind of annual cycle evolution of the daily rainfall, which also tells you how the ITCG itself moves on a daily time scale. This is associated with it's something called the tropospheric temperature. Suppose I take the average the temperature between 700 hectopascal and 200 hectopascal, and then average them between 30 south, the whole region, 30 south, 30 east, and 110 east here. So whole region, if I average the tropospheric temperature, then and plot it with time, what do we see? That there is a warmer condition to the south before the monsoon onset takes place, and the atmosphere is warmer to the south and colder to the north before the monsoon onset takes place. Then suddenly during onset time, around June, this temperature gradient of the north-south gradient of the temperature in the atmosphere, not on the surface, changes, and it becomes positive to the north, warmer to the north, and colder to the south. And that remains during a monsoon time, and then retreats back. And again, by about end of September, this becomes warmer, and then this part becomes warmer than the north, and therefore the gradient changes. So there is a relationship between the onset of the monsoon, which we will discuss later in more detail, that the tropospheric temperature gradient change has a relationship between the onset of the monsoon and the maintenance of the monsoon during the time, during the period, and then withdrawal of the monsoon and return to the winter conditions. So that also we'll discuss. So this all is related to a notable feature of our monsoon is of course what is called an onset. This is often known as a sort of singularity of that annual cycle. So in a way, there is some sort of a singularity here in the rainfall. This is a low-level jet. This is the winds over the Arabian Sea, averaged over a box and was plotted. So this wind also suddenly increases from here to here in a very short time. And that is the singularity. And that on a given year, if I had, so this monsoon strength is very much related to these, let me go back to one of this figure here. Sorry, where was that? Sorry. I have not shown the mean rainfall. Okay, we'll come back to that in a minute. So if I take there is something called low-level westerly jet. That means these winds at 850 millibar, about 2 kilometers over the Arabian Sea, is very strong during the monsoon, which I'll show in a minute. But those winds are very weak before the monsoon onset or before starting the monsoon. And this is the plot of wind around 65 degrees east and 10 degrees north. And if I took the kinetic energy of that wind and I plot as an evolution with time, then just at the time of onset, it increases by a factor of almost 10 order of magnitude. Suddenly, it increases the kinetic energy, and then the kinetic energy remains high throughout the. There are of course some subseasonal oscillations, but then remains high, almost 10 times higher than before the onset, and then decreases during the monsoon. So decrease phase is rather gradual, but the onset phase is, so this withdrawal phase is rather gradual, and the onset phase is rather sharp. And this is also an important character of the monsoon. So we have to keep that. These are the winds associated with the monsoon. So this is the June, July, August mean wind. and these mean winds have a maximum here in the Arabian Sea, and it has a cross equatorial flow, and this cross equatorial flow goes and produces a large scale cyclonic vorticity over this region. And this is where this vorticity, this region where the cyclonic vorticity center is often known as a monsoon trough region. Our synoptic meteorologists are always interested in looking at the trough region, where this seems to be the kind of anchors the ITCZ over there, and that is the region where the ITCZ seems to stay, because of this large scale vorticity. Cyclonic vorticity provides an ambience where convective activity can sustain itself. So this is one important characteristics of the wind flow associated with the monsoon. In the upper level, 200 millibar, the wind is kept by the lower level cyclonic vorticity is kept by an upper level anticyclonic vorticity of the mean flow, and that upper level anticyclone is associated with strong winds closer to the equator, known as the monsoon easterly. So we have a monsoon easterly at the low level and the easterly at the upper level. So these two are also two important sort of characteristic features of monsoon. So onset, southwest westerly Z. This is Z because it's a very interesting. At some point of time, I will talk about why this is. You remember I mentioned the Gill's model when I discussed. If I put the heat source over there, I get cross equatorial flows nicely, the cyclonic vorticity, everything I will get. But I will not get this Z. This Z it will not produce. But the Z requires the mountains in this region, in the Arabia and Eastern Africa. There are some mountains, small mountains. Those mountains interact with these winds and produces some western boundary intense, just like in the ocean. And the reflection from this from the western boundary produces intensification of the western boundary current. In the atmosphere also, Rossby waves reflected from this in the form of short Rossby waves. Those short Rossby waves tend to produce dissipation because they are very slow in energy propagation. The slow group speed of those waves actually dissipate energy and intensify these westerlies, and that is how a westerly jet is produced. And in fact, some recent modeling studies have shown that the whole intensification of the monsoon in the historical period by about 10 million years ago happened when these mountains actually evolved. Before that, the monsoon, even though the Himalayas came up before that, monsoon winds were still weaker. And so there is importance of this in terms of and this is a consequence of this sterlisate, is a consequence of the monsoon itself, because monsoon produces a divergence at the upper atmosphere. That upper atmosphere divergence at 20-25 degrees north will produce equatorial flow at above, and equatorial flow, angular momentum conservation of those equatorial flows will produce acceleration of these winds, and that produces these easterlies. So these are also important part of the monsoon system, and these are convectively coupled, as I said, because okay, I'll stop in a minute. So these are convectively coupled because, as I said, these winds are strongly related with the rainfall. These, you see that these winds go around this rainfall produce. So if this rainfall produces a heat source, and the heat source produces a low pressure area over there. So there is a low, around the low, now around 20 degrees north, it is almost quasi-geostrophic flow around the low produces a cyclonic vorticity. And of course, the low will try essentially to pull these winds from the southern hemisphere, but crossing the equator, they will become southwesterly, and produce the cyclonic vorticity over here. So therefore, they are strongly coupled, and there is evidence from empirical evidence from all these that they are strongly coupled. Now, if I look at what is the vertical extent of these by plotting the meridional velocity, mean meridional velocity and mean vertical velocity, average over 70 to 90 degrees. 70 to 90 degrees is my kind of window where most of the activity takes place. So therefore, I take that and then if you plot this, so you get a sort of overturning circulation, which is expected. Of course, for depiction purposes, I have multiplied the vertical velocity. The large scale vertical velocity is almost 1 order magnitude smaller than the large scale meridional velocity, and therefore, to depict them in a sort of in a visible way, I have multiplied them by a factor. So basically, but the structure is correct, and I can quantify it without doing this by using the stream function, which I'll show at some point of time. So major characteristics of our seasonal mean monsoon is the wet summer and dry winter, manifestation of the annual march of the ITCZ from south to the north, south of equator to about 25 degrees north during northern summer. It has a deep baroclinic vertical structure. By what I mean by baroclinic is low level thing is opposite to the upper level. So there is 1 zero crossing here. That is first baroclinic mode. In the vertical structure, there is just 1 zero crossing. So therefore, that is kind of known as the sort of first baroclinic mode. So the structure is essentially a first baroclinic mode, and they are an abrupt onset. So any theory must explain these. And there is, of course, year-to-year variation. So I'll stop here at this point and then take a few questions. Then we'll come back and discuss these year-to-year variations in a little more detail. I'll also have to talk about some of the data issues. The rainfall data is essentially the basis for many of our long-term studies. And the rainfall data has always certain issues, and we need to understand them in order to remember the strength and the weaknesses of the rainfall time series. And that is something also I'll discuss in a minute. So let me stop here for a minute, and Anupam, maybe you can take a couple of questions.
So Professor Rama, you have a question, you can go ahead.
Yeah, I actually have two questions, if that's okay.
Yeah, sure.
So the thing is, so you said that these strong easterly jet is because of mountains and Rossby waves created by the mountains.
Westerly jet, huh?
Westerly jet. So the thing is that, do I understand correctly that the ITCZ is basically the place where the Hadley cell rises from?
Correct.
Yeah, and
correct.
so like that is being modified by Rossby waves and mountains.
Correct.
Is it possible to do a simple, or is it possible to read about a simple, like linear theory for this?
Yes, there is some very old, I don't recall right now, but I can give you a very old study where people did this. I'll come back to you on that. But
it
now
would be
there
nice if I
there
can
is
get a simple linear theory which can explain the basic structure of the winds. And my
linear theory, the basic structure of the wind is, there are two issues. One is, of course, the basic structure is, this is one of the basic structure, that cross equatorial flow and cyclonic vorticity of the mean wind is a basic structure. Okay, so but the additional structure is the jet structure here. Now this is an additional structure. So by Gill's model explains the basic structure, but it fails to explain the intensification of the winds in this region, and that has been separately studied by people not looking at the larger scale picture, but in just this intensification of these have been studied theoretically by some people way back. And there is some work on that, but recently I will give you a reference where the modeling study have shown what has and this actually I'm going to discuss that a little, in one of the lecture.
Okay. And my second question was, like, now if we look at this photo, the winds are all coming from the Arabian Sea.
Correct.
And this seems to be the pattern throughout the monsoon. So why is the Bay of Bengal important?
Oh, it is very important because because it is bringing these winds. The heat source is over here, but it is not very localized over the land. It is extended over to the eastern Indian region, right? Northeast India is a big heat source because there is a lot of rain. Okay, and there is Bay of Bengal, there is a heat. So the wind are actually trying to go around it, around both Bay of Bengal as and then goes towards north, because there is now mountains. The winds get affected by the mountains in the northeast, so it is not very clear, but it is trying to go around the heat source, which extends all the way to the northeast. Okay, and the North Bay of Bengal is an important part of that. So therefore, the winds have to go around it, and therefore now that is why they turn go here today, and then while it is going here, it is picking up moisture because this is warmer region. This is the warmest region, and there's so it, and it's bringing a lot of moisture to this region, and therefore the winds picking up here. Also during monsoon time, this part becomes cold, but this part is still warm, so it is bringing in a lot of warm moisture. That moisture and picks up more moisture. So when it comes here, there's moisture laden. The air is have a lot of moisture, and that moisture is the source for our convection. Therefore, the longer that it stays over the ocean, more moisture it picks up, and that is important. So therefore, it is sort of, you cannot decouple it, because the rainfall takes place over there, and the rainfall itself then pulls the winds around it, and while it is coming, it is bringing also moisture and feeds back into the rainfall.
Right. Okay. Okay, thank you.
Professor Narasimha, you can ask.
Professor Goswami,
Yes.
first I apologize. Sometimes if you feel that I am a little bit rude and harsh, I apologize. Okay. Please do not feel bad. That is a old TAF or custom of some of the people. Difficult to remove it. All right. Now the thing is, okay, I have two questions. The first is, you have shown the temperature and the wind profile, these graphs. Do you have similar thing for pressure at some height?
Yes. We have.
See, the thing is,
yeah.
Oh, you are going to show it later, or what is the thing?
I'm not
Even if you are saying, in that case, if through them or directly, if you could send some of them to me, it will be very helpful.
Okay.
See, the thing is that any small pressure change, even at 1 part in less than 1 part in 100, it can immediately drive winds. Simply because the dynamical time and this pressure gradient problem.
Correct.
So that is why the thing is that any information about pressure fluctuation, any of those profile, if you have, I should be most grateful if you could send it to me. Because there is no reason to go into the details here, because some of those things, it may not be part of your...
It is quite obvious that, sort of, because this is suppose the tropospheric temperature is warm by several degrees in this, the whole column of the air has become warmer. Warmer means lighter. So therefore, the pressure in this region is much lower than pressure in this region. And
no. But the problem is that the pressure equilibrium at a given height, it can be obtained in dynamical time scale, or wind will manage it. But the thing is that what you have shown about this temperature and wind part is much more profound. That is where I will put a small comment after my second question, or right now, because this is something, I suppose once upon a time Rama somewhere mentioned, Rama should correct me. Suppose as an example, the Bay of Bengal, where you have large number of that is rivers, continuously give you fresh water.
Yes.
Suppose you prevent it, and the salinity changes. Because of that, what you mentioned about the evaporation and these things change.
Absolutely.
Though over 100-year time scale, it may not show much. In the long term, some of those crucial things that you showed there, that might get modified. In a sense, whether it will be, and if so, at what time scale, etc. I think it is worth checking, but you people know it.
Yeah, yeah.
with
I
you
think no.
but
Thank you. Yeah, please go ahead. Please finish it.
okay, so this is the one point, namely,
Okay.
very specifically,
Okay.
given that Bay of Bengal, there this wind getting the moisture. If because of any reason, whether what we do in the water flow leading to this Bay of Bengal, whether from our side or Chinese side, Brahmaputra.
Okay.
That is one thing. Of course, other is in the land what we do. That is where the next question I am going to ask. So in that sense, well, right now, if you have any comment, advice, it will be useful. Yes.
Okay, so I'll just the second question about salinity. I think you are absolutely right that the Bay of Bengal is a region of is a very fresh water, and that is why it affects the fresh water, affects the vertical structure of the stability of the ocean, and therefore the upper layer is very shallow. So the shallow upper layer produces, so it becomes warm because the solar radiation, and this warm solar produces evaporation, and that evaporation then produces this lot of synaptic activity here. Lows and depressions are formed in this region because of the shallow mixed layer, and then mixed layer it takes away the energy, but then mixed layer again becomes loaded, and therefore a recovery time is short, and therefore more and more disturbances take place over there. And even if it then cools down the mixed layer, again it warms up, and then it produces more disturbances. So therefore, the fresh water in this region is very much important in terms of producing the rainfall maximum that we had seen there. For example, this rainfall maximum has a lot of sort of bearing on that salinity. Now, suppose you increase this salinity, and then the mixed layer will be now deeper, and then there will be sometimes it will form. Then the frequency of occurrence of these depressions and low pressure areas will be decreased, and therefore the total amount of rainfall of the monsoon will also be affected. So there is a dynamical thing that we can think about how the change in the, if we do a lot of decrease the river discharge or affect the by dam and other things, or by whatever human activities, that will have an influence on the activity of convective activity in this region, and thereby affect on the rainfall of the region itself. So that is one thing. And of course, as you said, the time scale could be much longer. It is not going to happen over a short period of time. But people have shown by doing modeling experiments that that is likely to happen if we substantially change the salinity of this region. So that's one response. What was your last question?
It is just, you see, as the wind flows on the ocean, you have already mentioned it, more and more water vapor it can take.
Correct.
And also a little bit slowly heating up, increased velocity. The moment it hits the land, no longer it gets that water vapor.
Correct.
But the land heating, and its direction changing. So in that sense, the moment you have this East African, the land specifically that is like hills there, they are not very, that is
very tall. Yeah.
Small, no, though not very tall. Some of them do go to, in the Congo region, I think even 4,000 meter, a little bit interior. But anyhow, you know those things much better. And the moment from there it goes northward, the Arabia, etc. region. So in a sense, the question is that you expect the wind to, that is in the surface, certainly this change. My question is that if you go to troposphere region, do you still have about the wind pattern like this, or it is very different?
It will be different because of this structure, the vertical.
Yes.
As we go up, the lower level, we have the strong winds, cross-equatorial fringe, and the cyclonic vorticity. As you go up, it will become like somewhat weaker. At about middle level, it will change sign. And so, and then it will be the upper level winds which are cyclonic, anticyclonic vorticity like this. So there is a vertical structure of this, which I have not shown you in great detail, but
Okay,
I have just shown these two levels, which indicates, and also this gives you an idea that sort of it goes and then changes sign in between and then sort of reverses in the other direction. So there will be a difference as you go into different layers. The wind will change sign, and the middle level is there sort of more or less no wind, kind of weak wind in that middle level. Okay, then I will.
Okay, thank you so much.
Thank you. I will continue. Is there
Professor
more
Goswami, you will attend to other questions at the end, is it?
How many more questions?
Two more questions are there.
Two more questions. I can take one more question, maybe.
Okay, so HP wants me to read that question. The question is, how or in what way tropospheric temperature gradient 700 to 300, as you have shown, leads to sudden monsoon onset?
I will discuss that in great detail in one of the the monsoon model. When we discuss monsoon model, I will discuss that in quite because the point is that very quickly I can tell you. So what happens if this is at the time of before the onset, the troposphere is warm here. And now consider troposphere to be warm. That means that there is a high pressure here, a low pressure there, and therefore the low pressure here, high pressure there. So therefore the winds are moving from north to south, and therefore northeasterly. So the winds were, that is the before the monsoon, in the winter monsoon, the winds were from the northeasterlies. And that is because the pressure gradient in the north-south was different because of this temperature. At the time of onset, the heat source has gone to the north. Once the heat source has gone to the north, now the winds have to go. There is a low pressure there and a high pressure here, and it is in the atmosphere, not in the boundary layer, but in the atmosphere itself. And therefore, over the boundary layer in the free atmosphere, now the winds are going to go from south to the north, and thereby cross equatorial flow and cyclonic vortices. So therefore, the monsoon starts. And therefore, there is a very strong link. It is linked, the tropospheric temperature has a linkage with the heating of the atmosphere, and the heating of the atmosphere is linkage to the pressure gradient, north-south pressure gradient, and that pressure gradient actually changes the wind. So there is a strong connection between the tropospheric temperature gradient and the onset and the withdrawal. Withdrawal time, again, the heating becomes south of that, the maximum to the south and minimum to the north, and therefore again the wind will change, and that is why they are linked. I will discuss that in more detail in the other talk. So okay.
So Professor Goswami, you'll take the other question at the end.
Right, I'll take the other question at the end. Okay. So let us move on then. So this mean condition that I mentioned has its own year-to-year variations. Now, if you look at the rainfall for 2 different years, for example, this is just giving you some example or feeling about how the rain changes from in a drought year, for example. 1987 was a drought year, and this is the distribution of rain, total rain during the June to September. And this is a flood year. 88 was a flood year where there is a lot more than normal rain. And if you take the difference between a long-term mean, we get the anomalies. It's the anomaly structure. So in a drought year, you see that the anomaly, the negative anomaly, was sort of negative everywhere in the ITCs. The ITCs itself was weak. So, and the fact that over the land, a very large region had negative anomaly or the below normal rainfall. And in a stronger monsoon, the ITCZ tends to be stronger than normal, and therefore the monsoon also becomes stronger than normal. And a larger part over the land, a larger area over the land is now above normal. So normally the extreme monsoon years have the anomalous rainfall has a larger spatial scale, And that is something that we need to, but on a not these are sort of extreme years. Not in a normal kind of years, there can be a lot of spatial variability, but on extreme years tend to be, the anomalous conditions tend to be much more homogeneous. And this is another example of 2002, which was also a drought year. During that time, during that year, there was a huge below normal condition on a daily scale. This is known as a long break in the monsoon. And when there is a long break, it tends to be, the seasonal mean tends to be much below normal in the large part of the country. And so this is the difference between the actual and the climatology, normal or climatology. So this is something giving an idea of just of year-to-year variations. Now, we have been fortunate to have a large number of rain gauge stations in the country, which was started by British, and based on such a 306 fixed station network, Parthasarathy et al. These are some people from IITM, B. Parthasarathy and his colleagues constructed a monthly mean data over the country on each of the stations, and from that monthly mean data, they create a subdivisional. There are all these are meteorological subdivisions of India, and you could make subdivisional means and then all India mean, and that data set has been sort of a benchmark data set for studying year-to-year variations. And I'll talk about the strength and weakness of this data in a few minutes, but based on this, many people have studied the year-to-year variations of monsoon rainfall over the country. And that I have taken some results from an article written by Sukla in a book, and I'm reproducing some of that here. And these are the different subdivisions and and some examples of rainfall anomalies, normalized anomalies in a drought year. This is 1877 is a huge drought, and 1961 is a huge flood year. And so if you look at the anomaly, again, as I showed 2 years, and these are the negative anomalies normalized by their own standard deviation. So 1 standard deviation below normal, 3 standard deviation below normal, etc., and so on. So large part of the country was negative. So when there is a huge drought, large part of the country is deficit. And there are few subdivisions in the northeast are positive. Similarly, in the pre-flood years, it tends to be the large part of the country is positive, but a few subdivisions in the northeast can become negative. So there seems to be a east-west dipole kind of variability in the year-to-year variation of the monsoon. And this is again seen from 2 other years. Again, this year is a drought year. So there are few subdivisions where positive anomaly, and the other subdivisions have negative anomaly much to the west. And similarly, the reverse takes place in the in a flood year. So this is another characteristics of year-to-year variation. The northeast tends to go out of phase with the rest of India. So this is something, but this is not a very strong anti-correlation, but there is a tendency for northeast to go out of phase with the. So summarize this statistics of this year-to-year variation is that the mean rainfall is about 85 centimeter. The standard deviation is about 83 millimeter, which is about 9.7, 10% of the mean. So lowest rainfall, it can be as low as 607 millimeter. Highest could be as large as 1017 millimeter. So the lowest rainfall is like 2.7, 2.9 standard deviation below normal, and highest rainfall is 1.9. So highest rainfall, the floods and droughts are somewhat asymmetric. The extremes on the floods tend to be less intense compared to the extreme droughts. So this is another important characters why we need to understand that. So in another way to represent the variability is, so this is the mean rainfall again in terms of centimeter, and there is a large rain in this region and the low rain in this region, western part. So the rainfall, mean rain actually decreases from the east towards west, and of course Western Ghat there is large rainfall here. So and of course in there is a dry area here in the Tamil Nadu region due to the rain shadow effect from the Western Ghat. So this is also something that we need to remember. And if you look at the coefficient of variability, individually, the coefficient of variability, that is the standard deviation divided by mean in terms of percentage of the mean, is generally about 20% of each of the subdivisions. But where there is heavy rain, the coefficient of variability is low. But as you go to low rain, mean rain region, the coefficient of variability. So variability, year-to-year variations is much higher where there is a low mean rain. Same thing happens over the Tamil Nadu region here. So the variability and the mean are sort of inversely related. So this is also something I think this is a sort of general characteristics of the rain itself, which seems to follow something called a gamma distribution, and therefore the mean and the variance have a relationship. So this important thing that I want to spend a few minutes in talking about the rainfall data sets, because rainfall data sets have been used extensively to study, but there are certain rainfall data sets which have certain issues we need to remember in terms of quantifying these signals. This Partha-Sarati data set is one of the best data set to study interannual variability. That is because it is based on what I call a fixed rain network. What happens is that rainfall has a small scale, lot of small scale variability. Like your mesoscale systems and thunderstorms have so small scale, there are a lot of variability from place to place. Now, suppose you have a network which is varying from one year to another year, one day to another year, your data daily means are calculated from different rain gauge stations. Then you can, by sampling, you will get some spurious variability will be introduced into the mean also, because if your network is varying every day or from one year to another year, therefore the seasonal mean itself can introduce certain spurious variability due to the sampling problems. Therefore, it is important to have a fixed network, and every day and every year you calculate get rain from that network only. And so even if you have missed some data, you are not missing the you are not adding any sampling problem. So your mean may be affected by that total number of rain gauge stations, but your variability will not be affected artificially. So that is why it is important. This data set is very they realized that, and they created it a very fixed network data set, and this I consider as kind of gold standard for studying internal variability. But it cannot be used for daily extreme, because there are only their monthly mean data, because many of the years their monthly data is based on only 10 days data or 15 days data, and there are a lot of gaps, and therefore although the monthly may not be affected so much, but not 10 days, but about some there are gaps in the months not completely filled up. But if we want to study the daily variables like daily extremes, then any gap in this data will be very bad, and therefore we'll have a bad statistics. So it is inadequate to study daily extremes. Apart from that, this is a very good data set. But there are many other data sets that have now come up, and these there are two other data sets that Santaki et al. They have created a longer data sets. Now they have 316 stations during this period. But before that, there are not enough stations that even that more than that station data was not available. Therefore, the number progressively decreases earlier to that. But then they did a clever bias correction and comparing how the smaller number of stations actually correlated with the mean at the time when the data was available, they are able to correct the bias and therefore construct a time series which is much longer, which is still very useful for internal variability studies. Again, this cannot be used for any extreme event studies or that. So for internal variability studies, we have a longer data set now available. Now, Professor that I have already said, and then there is also these other things, the Asian landmass data called Aphrodite data, and that data set is also very good because now it can, with monsoon rainfall, how the other rainfall in the other regions of the land, at least we know. That you can go backward from 1951 to 2015. So this is also good. But over India, it doesn't make much of a difference because only IMD data has gone there. And over Northeast, these data sets don't have enough stations covering for a long period, and that is a problem. So then recently there are two other data sets that have been added and by IMD, and these are very valuable data sets. These are daily data sets. They are gridded into 1 degree by 1 degree grid or at quarter degree by quarter degree grid. So data have been analyzed into these grids, and this Rajivan data is again a fixed station network data, and it is excellent for studying even the extreme events as well as internal variability for this period. It's a shorter period, but it is good. The pi-atal data, however, is a similar period, but it's a higher resolution. But it has gone for all the stations that data is available, and so that data is essentially a variable network data. So in the recent years, the data density is quite high, but in the earlier years, data density was poor, and therefore there is a variable sampling problem maybe there, and therefore internal variability study and other things, even the extreme event studies, the sampling might give a problem, and this. Especially for extreme event studies, I think this data is not very useful. But for studying some of in the recent decades, studying the spatial structure of, let us say, synoptic events, mesoscale events, etc., rainfall associated with them, these data will be very, very useful, but may not be useful for studying some of the things that I'm talking about in the climate sense. So this is the kind the data density that have changed from about 1500 to about 4000 at this, then again decreased in the recent times. And this is the network. It is at Northeast, it looks like there is a lot of data, but this data actually extends only for about 3-4 decades. But before that, when you go, there are very few stations on which daily data is available. And that makes the Northeast actually a problem. In this Rajivan data, Northeast only about 7 or 10 station data is available. So therefore, again, studying extreme events in the Northeast is also a problem from the Rajivan data. So, but over the India, you see, this is a very good data set of the rest of India. So each of these data sets have their own problems and strength. And in the Northeast, this data have a very large problem, most of the data. And you know, the Northeast represents a very large heat source, a large part of the monsoon heat source, because there is the mean rainfall is about 3 times the mean rainfall over the central India, and therefore it's a big component of the heat source. And the partiality data has about 12 stations which covers these. This is adequate for internal variability studies. But the gridded data have only about 10 stations prior to 1901 to 50. So therefore, studying these mean as well as extreme events becomes inadequate in the early part. In the recent years, maybe 4 decades, it is good, but not beyond that. So these are some of the issues that, so we recognize that there is a need for constructing a good daily data in this Northeast region, because this Northeast region daily data over a long period of time was not available. So one of my colleague in Cotton actually spent a lot of time trying to construct such a data set, and we have done a 90-year construction between 1920 and 2009, daily data based on 24 stations in this region, and this 24 station data is much more reliable now in terms of studying the extreme events and its variability. And when you look at the internal variability also, the larger network of data shows that the internal variability given by the other earlier these sparse network data are much more exaggerated, and therefore this is a problem. We need to studying the northeast internal variability. We have to be careful what data we use. And that is important because how the northeast rainfall is affected by other global parameters. We need the baseline data to represent the basic the internal variability, and at least this data set now provides a way of looking at that. So this is some of this thing. Some of this data is essentially presented in one paper recently. So with that, let me go into a little more about the internal variability. So the internal variability is as I mentioned, the special structure of the internal variability. So this is a long time series, as I said, by combining that Shantake et al. Data and Patrasarate et al. Data, we can now construct a pretty about 200 years rainfall, seasonal mean rainfall data sets, and that data set is good for studying the multi-decadal variability and internal variability. So, and that here I have noted down that I have already talked about some of this earlier, that the year-to-year variation of these are related to some extent related by to the El Ninos. These red circles are El Nino years. The blue circles are La Nina years. That is in the Eastern Pacific, warm Eastern Pacific, and cold Eastern Pacific. And then so there is a tendency for El Ninos to be associated with droughts or the negative side of the rainfall. On the other hand, the La Nina, the cold Eastern Pacific, has a tendency to be associated with positive rainfall. And that is interesting, and this is what is known as El Nino monsoon and so monsoon connection. So this was discovered by people like Sir Gilbert Walker, and then many people after that have studied this extensively, and we now know that there is an association between these El Nino, and I'll talk about that in little more detail in the teleconnection lecture. But here I just want to sort of point out that there is some association between El Ninos and El Nino, La Nina, and monsoon, drought, and floods. But you remember, but interesting thing to also remember that many of the droughts are not associated with El Ninos. Many of the droughts, for example, they are linked with something else. Of course, beyond that, the El Nino and La Nina definition is not very good because the SST data is not very good, so we have not done that. So similarly, many flood years are not associated with La Nina. Therefore, there is an association, but in addition to the El Nino and La Nina, sort of ENSO connection, there are other things that also affect the monsoon. So this is something that we'll discuss again further on this. I want to, another thing that we can see, if I take a sort of a 9-year running mean of this data, and that shows that in addition to these year-to-year variations, which are there is also some sort of a multi-decadal variation of monsoon. This is the multi-decadal variation of monsoon, which again we'll discuss in a little more detail later. So now Now, what is this sort of spatial pattern? I mentioned quickly. I mentioned earlier that the Eastern Indian, Northeast India tends to go out of phase. But how can we quantify it? So what we can do is we can use the rainfall data, the Aphrodite data, which has data over the land and from 1951 to 2014 or something, 2007, and use that year to June, July, August, September data for these years and do a special sort of empirical orthogonal function analysis. If we do that, you get these pattern. This is the first empirical orthogonal function, and this is the second function. So the first function indeed explains about 29% of the variance, and the Eastern India part goes, of course, out of phase. This is the main part of monsoon, and weak rainfall over Tamil Nadu, high rainfall over Western Ghat and Central Indian region. This pattern goes out of phase with this, and then there is, of course, a other pattern which is a little more complicated. I will not go into great details of that right now, but now we can ask. So there is the dominant pattern of internal variability has this east-west asymmetry or east-west dipole structure over land. Now, is this limited by the land data only, or it is part of the ocean system? Because there is a lot of rain over Bay of Bengal, but land data does not tell me how the rain is variability over the ocean is linked with this variability. So if I do a regression of this principal component on what is the satellite derived data, GPCP data over the land, it indicates that okay, this has an extension over the land. There is a ocean rainfall also co-varies with this, but there, because now you're allowing variability over the everywhere, because these are regions of very low rainfall, mean rainfall, and there is a lot of big variability. So that variability is the GPCP data sort of moves the variance, maximum variance, to be centered not at the not at not at the Western Ghat, but that moves over to the Gujarat region. So this is an issue, but indicates that okay, ocean rainfall also has a co-varying signature with the land rainfall. But suppose I take the ocean rainfall, the GPCP data itself, and then do a UF of the GPCP data itself. That data is available between 1979 and 2014, and that shows the dominant pattern is similar, and but the North Bay of Bengal actually goes out of phase with the Central India. So that is an interesting character, which there are many other studies also have sort of says. So there is a variability of the North Bay seasonal mean rainfall over the North Bay of Bengal is not is sort of out of phase with the land rainfall in this region. That is part of this northeast, becomes a part of the northeast rainfall center. So there are these issues. There is still some debate on this, but I think this is the kind of structure that we can get at this point with the available data. Now, the association of the monsoon with the El Nino has been studied in various other different ways, and one of the ways that one part of the El Nino and sudden oscillation is the sudden oscillation, which is a component of the atmospheric variability associated with the oceanic variability, that is the El Nino and La Nina. And in the atmosphere, there is a surface pressure variations in the Eastern Pacific and the Western Pacific goes out of phase, and that is strongly connected with the SST variability, and that is known as sudden oscillation. Now, if I define a sudden oscillation index, that pressure oscillation index, in terms of pressure between Darwin and difference between pressure between Darwin and Tahiti, and then you look at how they evolve in a strong, that pressure the index evolves during a low rainfall drought years and during a high rainfall or the flood years. It turns out that they seem to go out of phase, out of sort of opposite way, which is expected, and but indicates that, interestingly, before the monsoon season, there is some signature of these the sudden oscillation tending to go down and from positive to negative in the before the monsoon seasons, and during the drought years, the sudden oscillation index tends to go from negative to positive before the monsoon season, giving an sort of indication, sort of precursor to how monsoon may evolve. So this was used as a prediction precursor by many prediction models as the month during this period, the tendency of the sudden oscillation index. So this is a study. This is from a study by Shukla and Paulino, and this correlation, this relationship, seems to be changing. The monsoon and ENSO relationship seems to be changing in the recent years. So if I do a sort of moving window correlation between an index of El Nino, that is a sea surface temperature index in the Eastern Pacific, and the monsoon rainfall, that is June to September rainfall over India, and correlate them, and from these this relationship, if I just correlate these variations of these in a window of about a 31-year moving window or 21-year moving window correlation, and then shift it and go, and that correlation tends to be negative, which is what we expect, and it has been negative for a long period of time and quite robust, about 0.65, but in recent years that correlation seems to have decreased. Now, why this has decreased has been a subject of a lot of studies in the recent years and the debate, and we'll talk about that a little during the teleconnection lecture that I'll give. But I'll just point out that these are the kind of changes that is happening in the ENSO-monsoon relationship, and this is an important science question why it is. Another important part of the ENSO-monsoon relationship is that, suppose instead of doing, this is the simultaneous correlation. Now, instead of doing simultaneous correlation between these, suppose I take the monsoon rainfall as the basic index reference time series, and take monthly data of the El Nino index, the Nino 3 index, of the SST data, monthly SST data over that region, and correlate lead lag correlation of that. If I do, what it shows is that over the whole period of time, there is simultaneous correlation. It gives me over a long period of time. If I do, simultaneous correlation is about 0.5, 1.4, and then the maximum correlation between ISMR and SST happens not during the monsoon period, but after the monsoon period. So this is kind of intriguing, because about 4 months after this, when actually the El Nino signal also tends to be maximum in this time after the monsoon, during the next December, January, February, El Nino tends to be maximum, and that is when the correlation between monsoon and this also becomes. So this indicates that maybe monsoon also has an influence on the El Nino itself. So the connection between El Nino and monsoon appears to be two ways, not just one. And this is also a subject that I will discuss in one of the talks later on. So in terms of this, what is the temporal modes here? This variability have certain, you see that there is a lot of year-to-year variation of the monsoon. So one question, important question is, okay, is there some other temporal modes of variability? Like, is there a certain periods which are more dominant than others? And so we can do a power spectrum and look at that. And instead of that, we can do some sort of empirical or ways of decomposing temporal modes. So we used is something called the empirical EMD, called empirical mode decomposition technique, which is something which gives out what is called the intrinsic mode function as the individual empirical modes. And it is a kind of standard technique now many people use to decompose a time series, which produces a set of not fully orthogonal but nearly orthogonal functions and a complete set. This set actually the anomalies associated, when you sum up, you get the total anomaly, but they are nearly orthogonal to each other, and they produce separate the frequencies. The different modes have distinct frequencies, and it turns out that there is a mode which explains the monsoon. Statistically, significance of these modes can be assessed by doing some Monte Carlo simulations, and it turns out that this mode, which is a quasi biennial mode, about 2.7 years period, is quite significant, explains about 65% of the variance. And there is this multi-decadal mode with about 65 years, which is also statistically significant, but explains about 7 or 8% of the total variance. So there are several modes. There is one mode which is about 7-year period, 12-year period, 26-year period, and so on. So there are some decadal modes. So these two modes, this particular 2.7 year is partly related to the El Nino. El Nino also has a biennial component in it. It has a 4-year component, but also has a biennial component. So this essentially is the relationship with largely coming from El Nino. And so this is in terms of, again, this is information, and we'll see how we can explain that later. So these, of course, the monsoon internal variability has a lot of implications in our society and our food production. And this is a study by Gadgil, Professor Sulochana Gadgil and colleagues, and then they showed that if you look at the departure of the rainfall and look at the impact of our food production, this is the total food production departure, and this is GDP changes. So there is a very strong connection between total food production in the country and the monsoon rainfall. And even today, it explains about our, I think, economy still depends on about 20% on this rainfall variability. So this is the reason why we need to understand this year-to-year variations of monsoon very well. There are also several other factors that seem to have association with monsoon. I cannot go into great details here in this, and I'll just mention that there is a European snow cover variations where which is also have found some relationship with monsoon. The specific decadal oscillation. This is another oscillation of sea surface temperature in the North Pacific, which also seems to be related to monsoon. There is something like an El Nino in the Atlantic equatorial region that also seems to be associated with monsoon. There is something called southern annular mode, which is in the southern hemisphere, which also has a association with monsoon. These associations are recently discovered, more recently discovered, and there are certain details are still debatable. The physical mechanism between them are somewhat debatable. I will not go into great details right now, but I will say that that recently the snow monsoon relationship has been shown that and that the snow monsoon relationship is essentially apparently against like El Nino monsoon relationship is changing. The slow and monsoon relationship is also changing during recent years. So there are some of the issues. I'll just flag them here because we cannot discuss in great details. There is a Pacific decadal oscillation. My colleague Krishnan had done some good work on showing the relationship between these two. Again, the physical mechanism between these and the independence of these with the El Nino and Southern oscillation and association with the North Atlantic SST is not yet well established. And that is why we need to do more work on these relationships and the robustness of how much they contribute to our variability of the monsoon, quantify that more clearly. And that is what is required today. And this multi-decadal variation, we'll discuss this multi-decadal variation again. I flag it here. The multi-decadal variation appears to be quite important because it tends to modulate the flood and drought years. So if you take the different multi-decadal episodes, when the epochs there is a negative epoch, then you have 2 floods and then 14 droughts. This is a positive epoch of multi-decadal variation, then 9 floods and 1 drought. And like that, if you see, there's clearly in a positive phases of the multi-decadal, there are more floods and less droughts. And the other hand, there are the negative phases, there are more droughts and less floods. So they modulate the interannual variability, and therefore they are important in terms of because the interannual variability is what is important for our decisional prediction. To predict what happens next year, we have to have we have to be able to predict also how what phase the multi-decadal variation will be, and that is what makes the multi-decadal important. And now we are beginning to understand that this multi-decadal variation is associated with sea surface temperature in the North Atlantic. And this is a study recently done by some of my colleagues where they looked at there are these are the monsoon variations, and if you take all the drought years, some of these drought years which are marked by red are associated with El Nino. So this is an El Nino structure. So this is a composite of sea surface temperature anomalies associated with all the droughts which are associated with El Nino. El Ninos we can identify from this. Then we can find out how many droughts are there. Now take these years and average the temperature, and it found out obviously it shows a very strong El Nino kind of warm anomaly here and a cold anomaly here and warm anomaly here. And this is a typical structure of El Nino. Now you take the other year drought years, which are marked by blue here. Take only those years which are not represented by El Nino. Those droughts are these blue years. There are about 10 of them. Now, if I take those 10 blue year droughts, drought years, and again I make a composite of a global SST anomalies, it turns out that the biggest signal is in North Atlantic. So now it appears, and in the equatorial region there is no big SST signal. So this is a very important finding in the sense that so when there is a very strong equatorial SST anomaly, then this El Nino will control the monsoon. But when monsoon is actually there is no SST anomaly because El Nino is changing from is a period period of El Nino is, and so is about 4 years. So so it goes on changing from positive, negative, positive, negative. In between, there are times when El Nino goes through transition phase. And during those transition phase, apparently the North Atlantic SST can influence the monsoon. And that is what we have now figured out, how they can influence through an atmospheric. So if you do some sort of a the circulation composite during those years, and we find that there is a set of Rossby waves, stationary Rossby wave emanated from North Atlantic and affects the monsoon region through a vortex here, and that vorticity affects the lower level circulation, producing during this cold anomaly phase a anticyclonic vorticity in the lower region and the drought condition over the monsoon region. So we can now actually identify a physical connection through which these North Atlantic SST can link it to the monsoon region. So there is now, what is important is that if that is so, which is still there are some doubt questions which I will again address in the teleconnection lecture more detail, that if indeed these SST is forcing the droughts, all the droughts that are not affected by El Nino are affected by sea surface temperature in the North Atlantic, and the rest of them are affected by sea surface temperature in the East Pacific. Therefore, all the droughts are associated with slowly varying sea surface temperature, which are predictable. That means all the droughts are predictable. Therefore, that makes a big difference in terms of understanding the predictability of our droughts. Same thing possibly we can start also look at predictability of the flood years. So with that, I'll stop here and raise these questions. Basically, we have to raise these, from these, what do we know? We know that what maintains we have to ask what maintains the three-dimensional structure of the monsoon and provide a framework for understanding its variability. Because variability is the variability of the mean. First, we have to understand what drives the mean, and therefore that what drives the mean must have a link with what drives it. Variability also, therefore, that is very, very important. So I hope that I'll give some answer to that question in lecture 7 and the next lecture. Then on terms of variability, we have to ask questions. What is responsible for the quasi-biennial oscillations of the monsoon? Because that is a very dominant mode of variability. And what drives the multi-decadal mode of ISMR, and what is the teleconnection mechanism? I will try to provide some answers to that in the lecture 13. Then questions on teleconnections. How do they connect? The physical mechanism we have to understand. In addition to statistically understanding the relationship, we have to also physically, only then we can have confidence in the statistical relationships if they are connected with a physical mechanism. So what is the physical mechanism of ENSO and AMO influence on the monsoon? So I hope to give some answer to that in the lecture 9. So these are some of the questions we'll raise. Now, these are, I'll stop in about 5 minutes, just quick. So these have implications. The understanding of these, the importance of these connections, the ENSO, for example. The ENSO has a strong relationship with monsoon. Therefore, the predictability, some part of predictability of the monsoon comes from the association of the ENSO. Therefore, the model and for prediction of the seasonal prediction of the monsoon, we need a model, a coupled model. And the coupled models have their own, they're not never perfect, and they have their own biases. So how do these biases affect the prediction and predictability? That it will affect it, because once there is a bias, and that bias is going to manifest, bias is going to, suppose there is a bias in the mean structure of the monsoon rainfall. So year-to-year variation will be with respect to that mean monsoon of decline model itself. Therefore, their anomalies will also be affected by this, and therefore, when you compare that to observed anomalies, they are going to differ from each other, and therefore our skill of prediction is going to be poor. And therefore, the models have to minimize the biases of representing the mean as well as these teleconnections. So The models have improved, but there are some models have some very characteristic biases still remaining in the models, and that is something of a concern. And we did recently looked at some of the my colleagues looked at the recent models, including the CMIP 6 models, starting from CMIP 3 models to CMIP 6 models, and looked at how these the biases have improved or evolved. So this is we looked at some 27 CMIP 3 models and 30 CMIP 5 models and 30 CMIP 6 models. This is the observed rainfall distribution from GPCP, and these are the differences between these ensemble mean climatology CMIP 3 models, CMIP 3 models, CMIP 5 models, and CMIP 6 model from GPCP. It essentially tells you the biases. So this is negative. So which means that over the land going up to the North Bay of Bengal, this region tends to be drier in the models compared to observation. So this is a generic problem that has persisted even in the recent models. It has reduced considerably, but still persisted even in the recent models. And then over the ocean, there is there is warm bias, wet bias, and over the land there is a dry bias. And this is a sort of a problem, because this is what is going to limit our and so we try to understand what is actually happening, and we found that so over the years, these different types of models, this is a correlation between the pattern of mean rainfall over Indian region, climatological simulation of the mean rainfall by different models and observations. It turns out that the correlations were like 0.7 or so in this, and there are more than 0.8. There are only 3 models which could get good correlation. But as the models have improved, the number of models increased in terms of higher correlation with the observed. And in this latest model, actually, we have about 15 models which have much better correlation. Also, with the higher the interannual variance. This is the standard deviation of the simulated interannual variability, and that has come closer to observations in these new models. But in the earlier models, they were very much underestimated, and slowly that has improved. So models have improved, but there are still some biases that are important. So models are definitely improved, but we need to work on this bias. Now, where did these biases come from? We looked at that the best of these 15 models. If I take those best of the models and do the mean and take again the difference with the GPCP, still there is a cold the dry bias over the land. But this dry bias has reduced, but there is. But if I look at that evolution of that spatial distribution of that with latitude, what turns out is that this is the observation. So if I average between 75 degrees and 90 degrees east in that longitude band and plot the rainfall simulation with the different ensemble mean of the different the CMIP 3, CMIP 4, CMIP 5, and CMIP 6 models, and this is observation. This position represents the ITCZ to the north. Okay, the higher rainfall. So this is about 23 degrees. But most of the models, even the best of the CMIP 6 model, produces the ITCZ somewhere around 10 or 13 or 14 degrees. So somewhat to the south, and these or 15 degrees. So about 8 or 10 degrees to the south, and that displacement of the ITCZ position gives rise to this dry bias. So fundamentally, the models have to improve the simulation of the ITCZ, and that ITCZ has its own dynamics, and that we are going to discuss in lecture number 7. And I think this is how we have to improve. Why the models are? We have to understand why models are actually is systematically producing ITCZ, not going to 23 degrees north, but going to only about 15 degrees north. And that creates a dry bias over the land, and that has implications in terms of prediction and so on. So so this is where the models come in and the improvement of the models, and this is where the models improvement is required. So with that, I'll stop. There is also differences in the teleconnection between the simulation of the teleconnection between and so ISMR, but I'll not go into great details at this point of time. Let me stop here